Good evening, everybody. Hopefully everything's working fine now. So, we're back working on Project Longshot. Last week we were doing a lot of fun stuff, getting a lot of the basic input to work, and sort of drawing and moving about. So today we're sort of going to do a little bit of continuation on that at first. Just a couple of small little things to get out of the way. Then once we're done with that, plan is that we are going to try and separate out a little bit of the world model. We're going to start by defining sort of a chunk, which will be a portion of the world in 3 dimensions. And then we are going to see if we can't generate a very, very, very flat chunk, and see if we can't generate some quads or some cubes and texture them. At least that's sort of the hope. But first, we want to fix one sort of slightly annoying thing, is that currently, once last time we set up so that we can grab a pointer lock, and we can move this view nicely around without like having a mouse cursor showing or anything. So the first thing we want to do, or rather the problem here, is that I can hit escape to escape that pointer lock. You'll see my mouse cursor is all of a sudden back. And now I can only move within the window, but I can't get that pointer lock again. So what we want to set up is so that when we lose pointer lock, we queue up another request to get that pointer lock back. So Emscripten luckily has these sort of pointer lock change events, which will tell us whenever the pointer lock changes, whether or not we have it or not right now. And then if we don't, we're going to want to queue up another pointer lock. So let's just quickly switch over to the code. So this is our input class from last time, and here we request our pointer lock. So what we want to do is we want to set up another callback. We want something along the lines of Emscripten. Set pointer lock change callback. So again, we don't have any particular target in mind. We have this as our user data we want to capture. And then we want to use sort of a pointer lock change callback. So we just quickly need to define that name, and I don't seem to have the header file open, so here we go. So yet again, we're doing with the static bool pointer lock change. Takes the event type, and then we take a const. This will be an Emscripten pointer lock change event, and a void pointer, which is this pointer when we get it back from the callback. So to implement that, take the pointer lock change event, not clearing slash sync. Okay, it's probably still parsing. So what we want to do is, if our event here tells us that is active is false, then we are gonna once again request the pointer lock. So let's try and compile that. And apparently I am failing somewhere. Has to be a pointer. Try that again. So now, hopefully, if I let it grab the pointer lock, and then I escape it, and then I go back in. We again get the pointer lock. So whenever I hit a key here, I'll re-grab the pointer lock. Great. So now we are gonna work on the idea of a chunk. So we're gonna start by creating a class called a chunk. There we go. Now, once we have this class, we can then define a chunk. So some of the things we are going to want to work on is sort of defining a size of a chunk. So at least initially privately, probably, or actually publicly, we're going to want to be able to see that from elsewhere. So what we want to do is we want to have a counts expression which is of size type, which is going to be the dimensions. And to start somewhere, we're just going to say a chunk is 32 by 32 by 32 blocks. So we'll pull in the definition of size t. Now, for a chunk, we are going to have a constructor, which is going to construct all of this. We're going to maintain some data about our chunk. So we're going to have the idea of a block, and we're going to do it this sort of the hackish way, and we're going to say that a block is just a 64-bit integer, and we're then going to later worry about encoding all kinds of information down into that. So far we're just going to say 64-bit integer is what a block is. So we'll just pull in that definition as well. So we are going to have a standard array. This is going to maintain our block data. It's going to be full with blocks, and it is going to be dimensions, because we only have 3 dimensions. We're going to call it size. It's going to have size by size, size by size by size blocks in it, and we'll just call that blocks. We can pull in the definition of array as well. So what we want to do when we create a chunk here at first is that we are just going to go and set. So again, we're going to index this sort of x, y, z. So privately, just to help us out here, we're going to have a couple of setters and getters, or at least one. So we're going to set a, this is going to be a block underscore t, block type. Matches the standard library and allows me to call this parameter block. And then we are going to go for coordinates here called x, y, and z. This will set that block to a given value, right? So when we have this function, so we have the chunk set. Okay, apparently I've been spelling chunk very wrong so far, so we'll just try and quickly see if we can't correct that. Okay, I wasn't really planning on calling it n either. One more time. Chunk. There we go. So we have this set block function. We are first going to start by calculating our index. So we are gonna sort of index this x, y, z. So we take x times our size times our plus the y. Multiply this by the size and add the z coordinate. Then we index our blocks based on this index and assign our block to that. Nice little function here. So what we're going to do here is that we're sort of going to set the upper half to nothing and the lower half to 1, and we're just going to pretend that's like a block or something for now. So we are going to iterate over all 3 dimensions. So we're going to start at 0, and as long as x is less than the size, we increment x. So just the same for the other 2 coordinates, y and z. So if y is greater than size half, so we're in the upper half, then we're going to call set 0 x y z, and else we are going to call set 1 x, y, and z. So doing that, we get to assign sort of the air and whatever we're doing, just as a sort of primitive start here. So what we're going to do is we are going to go over into our main function, and we're just going to create we're going to do it in the main loop now. We are going to create a chunk. See? Need to import that. And then we are going to create we'll take a look at that later. So now we should be able to create our chunk. Now, what we'd kind of like to do is we'd like to render a quad or a cube every time our chunk is not 0. So we can either make the chunk know how to render itself, or we can make a class that takes a chunk, creates a renderable, or something that can be rendered. And I think we're going to go for the latter of the 2 options, because that way if we need to change the render at some point, say we move to Vulkan or something like that, we don't have to change the chunk structure. And also if we're doing like a server backend, we can just omit the entire rendering area of the code and it won't even need it. So we are going to make a new class. It's going to be called a chunk renderer. So what we're going to do is we are going to start by going over into our TLES renderer. We're going to introduce a class here, which is going to be a TLES renderable. And we're going to worry about what that is in a little bit. But for now, our chunk renderer is going to inherit from this renderable, because the chunk renderer is renderable. So our chunk renderer can be instantiated on a chunk by reference, because we should not need to change not a chunk renderer, the chunk. There we go. Again, chunk T might have been a good idea. Again, because we don't want to really change the state of it, we're going to go for a const thing here. Then we're going to have a private. Keep a reference to the chunk. Probably gonna complain about the reuse of the name. No, apparently not. Great. So what we want to do is, so a renderable essentially is an interface, or a pure virtual class, also known as an interface. So what we do is we have a virtual void function called render, which will be responsible for rendering, and we're going to mark it as pure, as in never instantiated. So now we should not, we're not instantiating a chunk renderer anywhere. But what we want to do is we want to modify our GLES renderer to, in addition to the camera, what we want to do is we want to take a standard vector of, well, essentially pointers to renderables. And this is going to be sort of our render list. This is what we want to render. Complaining about a missing include, but I think that's done. There we go. So this is going to be added to our GLES render here, our render function. So we set up a lot of stuff here, and we already have the concept of a, sometimes I should take a look, we have the concept of a block already here, which is sort of a renderable block in some sense. We're going to take a look at whether we want to keep that or not. But anyways, what we want to do is we want to say, instead of rendering just this one thing, we are going to do a loop over the render list. So for every renderable in the render list, we are going to add the renderable to render itself. These are pointers. So now we can't call render like this, we have to have a list of renderables. So the chunk itself is not renderable, so we need to create a chunk renderer R, instantiate that from our chunk, and then we are just going to create a list here pointing to R. So that should compile now. Apart from that, the chunk renderer is an abstract class because we haven't implemented the render method. So what we want to do is we want to go for a chunk renderable here. And we want to say, okay, this thing has a virtual void render function that can be called, and now we should just get an undefined error or an unresolved symbol. So this is, we can't find chunk renderer render chunk, where the render part of this is probably saying virtual method 1 or something like that. Or no, that's the constructor. Yeah, we haven't defined that either. So we can start with the constructor, because that's relatively easy. All we want to do is initialize our local chunk based on the constructor argument. And it needs a little bit of help because this is the class chunk and not the variable chunk. Great. Oh, good point. So when we have this one, is it GLES renderer here? So when we have this renderable, we are also going to want to have, actually, we don't technically need a virtual destructor, but consensus is that it's kind of a good idea. So we are going to want to go over here, and for our GLES renderable, we want to define the destructor as the, wait, can I not just say that this is just the default destructor? If I could spell default default. There we go. Seems to work. So now we need to define the chunk render function. So we already sort of have the same idea over in the block. It has these wonderful vertices and indices, which is what we want. Now, this is where it gets a little bit interesting, because we're doing like this draw elements triangles. It would be really, really nice to be able to just emit one draw elements call and then draw the entire chunk using the right indices and the right vertices. Issue is that we're mainly drawing squares to make a cube, and this thing takes triangles, but or triangle strips or triangle fans, which are sort of continuous triangles, but we'll have to emulate that with triangles. But the thing is, we can actually sort of, if we're a little bit sneaky, we could allocate and populate sort of a standard vertex buffer, which every chunk will just use, and then we just have the local indices, sort of what are the actual triangles that we're going to be drawing for every single chunk. So that way we can hopefully sort of the vertices will be the big part of the memory usage, and we can save a lot on sort of on the memory usage by sharing these for every chunk, and then just having the indices for each chunk once. So that we have this once and this per chunk. But I'm not about to write every single vertex for a chunk, because there are a lot of them. So we're going to want to generate this. So rather than having a static vertex, so for our chunk renderer, what we want to do is we want to have a static field, which is going to be a static. We're going to make it an array, and we are going to have it as GL floats. We probably need an include for it to be able to recognize the idea of a GL float. Include GL GL ES2 slash GL2.h. So we have the concept of a GL. It's not really auto-completing for me, but no worries. We have GL float here. So this is going to be chunk size +1, because we have 32 chunks in a row. That means that there are 31 sets of vertices, because every block has a vertex on every side. Just like if you have 32 pieces of fence, you have 31 fence posts. So we have that on each side. And then we have 4 floats for each. And we're going to call this our vertex buffer. And then we are going to just quickly save whether our vertex, well, yeah, whether our vertex buffer has been initialized. We're gonna see if we can't default that to false in this case. So we don't have chunk included. That's because it's a class. So result from the root namespace. I'm again not really spelling chunk very well. Guess something else has gotten stuck in my fingers. And I am not allowed to initialize this out of line, or must be initialized out of line. So over here we have our bool vertex buffer initted on the chunk renderer, and we're going to initialize it to false. There we go. So what we're going to do is if we do not have our vertex buffer initialized, then we are going to generate the vertex buffer. So this is going to be a static function. Like this. And what we are going to do is we are going to go for we're going to generate the vertex buffer surprise. Renderer generate vertex buffer. There we go. Probably spelled something wrong somewhere. And why are you not capturing correctly? There we go. So what we want to do for this is we simply want to run through and generate a hell of a lot of vertices. So what we want to do is we want to run size our x coordinate from 0 to the, we want to go to the, as long as we're less than or equal to the chunk size, again, we want to generate one extra one on each side. We then increment x. So we walk through that. Again for y and z. So at this point, what we want to do is we want to generate our vertex. So for our vertex buffer, we are going to index it as, again, same way we did for the chunk. So we have this same type of index. Major difference is that we have 4 elements per piece. So we need to multiply that by 4 and then offset by that. And this again is our chunk size. So for the x coordinate, we are going to go for the x, but we are going to subtract half the chunk size from it, because that way we will sort of have a chunk of 32 blocks going from -16 to +16, so the chunk will sort of be centered around 0. Then we have the y and the z coordinates here, are the ones afterwards. So these are at offsets 1 and 2. Same idea, we want to center it. And then finally we have the w, or the projection scale, or what you want to call it, which is just going to be 1. So that sets up sort of our global vertex buffer that we can use for every single one. Now we also want to actually bind that to a vertex buffer so that OpenGL has it. So what we're going to do is we're going to go through this generation of the vertex buffer here. So we also need to save that globally. So we're just going to rename this to data because that's sort of the raw data, and then we're going to have this as the actual vertex buffer, which is a glint. So we're going to have lots of complaints over here. So we want to generate a vertex or a buffer in our vertex buffer. It's going to be an array buffer. Let me just check. Yeah, an array buffer because the other one is an element array buffer. So we are going to bind vertex buffer as an array buffer, and then we are going to go for our vertex buffer data size, because that's the number of elements we have. So the data is then our vertex buffer data dot data, and this is just static. We are never ever, once we've put all of this, we are never going to be changing it ever again. Okay, fair enough. It's a GL, and again it loses the capture. Weird stuff. Anyways, it's a GL uint. So we have unresolved symbols. These two don't sort of belong anywhere right now, so we are going to declare them over here as well. I'm going to say that the uint is initialized to 0, and the array will just be default initialized, meaning probably going to contain absolute bollocks. So let's just quickly try and refresh, and yep, no GL errors, which is what we like to see.